before learning this module, the users should be aware of origin of orthomagmatic deposits, genesis of igneous iron ore and origin of pegmatites. Objectives: to understand the mode of occurrence or orthomagmatic iron deposits associated with intermediate to felsic volcanic rocks, to understand the mode of occurrence of pegmatites, their mineral wealth, depth wise classification of pegmatites and diverse views on their origin. Following are the contents of this talk. It begins with introduction, followed by relationship between alteration, gangue and mineralization, reactions between WallRock and fluids, types of WallRock alteration and advanced argillic alteration and alteration assemblages. This includes serpentinization, intermediate argillic alteration, propylitic alteration, chloratization, carbonatization, potassic alteration, silicification, felspatization, tourmalinization and other alteration types. This is followed by influence of other rock types, then correlation with type of ore mineralization, timing of WallRock alteration, distribution of alteration assemblages, an example of WallRock alteration and followed by summary. Now, let us start with the introduction. The country rocks that enclose ore deposits of hydrothermal origin almost always show reaction effects that result from the tendency of hot circulating fluids to equilibrate with rocks flanking the conduits through which they move. Both the fluids and the rock adjust. The conduits become lined with a layer of insulation between fresh external rock and the heated, commonly slightly acidic circulating solutions. That layer of insulation is called WallRock alteration, and the volume it occupies is the alteration zone, halo or envelope or selvage. Alteration effects may be visible for as little as a couple of grain widths beyond vein wall, or they may extend for kilometers around a network of veins. Normally, the envelope around a vein of 1 or 2 meter in width is in the order of 10 to 20 meters, but many exceptions are noted. Some alteration is colorful and texturally and structurally flamboyant. Elsewhere, it may be totally inconspicuous. Many alteration halos show a zonation of mineral assemblages resulting from the changing nature of the hydrothermal solution as it passed through the wall rocks. The associated ore bodies in certain deposits, example porphyry type copper deposits, may show a specific spatial relationship to the zoning. There are two main divisions of WallRock alteration. They are hypogene and supergene. Hypogene alteration is caused by ascending hydrothermal solutions, and supergene alterations result from the descending meteoric water reacting with the previously mineralized ground. A third type of mechanism giving rise to the formation of WallRock alteration is the metamorphism of sulfide orebodies. Studies on hypogene alteration are important because they contribute to our knowledge of the nature and evolution of ore forming solutions, are often valuable in exploration and produce minerals such as phyllosilicates that can be used to obtain radiometric dates on the WallRock alteration and by inference on the associated ore mineralization. The study of hydrothermal fluids has shown that they are commonly weakly acidic, but may become neutral or slightly alkaline by reaction with wall rocks or by mixing with other waters, for example, groundwater. The solutions contain dissolved ions that are important in ion exchange reactions, and the composition of a particular hydrothermal solution will have an important bearing on the nature of the resulting WallRock alteration it may give rise to. Since the chemistry of wall rocks can also vary greatly according to their petrography, it is clear that predictions as to the course of WallRock alteration reactions are fraught with difficulties. Nevertheless, there is, despite a variety of controls, a considerable uniformity in the types of WallRock alteration, which facilitates their study and classification. The controls of WallRock alteration fall into two groups, governed by respectively the nature of host rocks and the nature of ore forming fluids. Besides the chemistry of the host rocks, other factors of importance are their grain size, physical state, example sheared or unsheared, and permeability, and for the hydrothermal solution important properties are its chemistry, pH, EH, pressure and temperature. Relationship between alteration, gangue and mineralization. Alteration mechanisms normally are completely continuous with and a part of the hydrothermal ore forming processes. Alteration is defined by any change in the mineralogical composition of a rock brought about by physical or chemical means, especially by the action of hydrothermal fluids. Alteration minerals can be considered as much the result of mineralization processes as are the ore minerals themselves. Nature of the alteration products depends on number 1, the character of the wall rock, number 2, the character of the invading fluid, which defines such factors as EH, pH, vapor pressure of various volatile species, anion, cation composition and the degree of hydrolysis, and number 3, the temperature and pressure at which the reaction takes place. The alteration halos around many deposits are more widespread and much easier to locate than the ore bodies within them. For example, the copper ore body at Morenci in Arizona in the United States of America is only 2 square kilometers in outcrop, but the readily mappable alteration zones cover an area of 6 by 12 kilometers or 72 square kilometers. Alteration effects may reach old or present surfaces, or they may be blind and found only in underground workings or in drill holes. Since 1970s, a great deal of work has been done in attempting to determine the exact relationship between various types of ore deposits and the alteration minerals that surround them. These studies focus on answering the following aspects: what types of alteration products are associated with particular types of ores? What changes are to be expected in the country rocks at various distances from the ore bodies? Where in the alteration halos are the ores most likely to be found? What directional aspects can be discerned? What can be learnt about the mass transfer and the geochemistry of the systems? Alteration may result from diagenesis in sediments, or regional processes such as metamorphism, or post-magmatic or post-volcanic processes associated with cooling, and direct hydrothermal mineralization processes. For example, propylatization is the result of low temperature, pressure, peripheral alteration around many ore bodies. Example, porphyry type copper deposits. The propylite assemblage consists of epidote, chlorite, MgFeCa carbonates and sometimes albite orthoclase, all involved in partial replacement of wall rock minerals. The same assemblage can be produced by saussuretization of mafic to intermediate volcanic rocks as a consequence of regional metamorphism of green schist facies. It can also be produced during cooling history of basalt, andesite, dacite pile. Hence, hydrothermal alteration that is surrounding the ore deposits can be confused with other phenomena and vice versa. In such cases, geochemistry can be extremely useful. For example, wherever bona fide hydrothermal propylatization exists, anomalous values of 100 to 400 ppm copper or zinc are common. Next, reaction between wall rocks and fluids. During wall rock alteration process, chemical gradients are most important, whereas temperature gradients are probably normally of secondary importance and pressure gradients are rarely significant. If it is accepted that chemical and thermal gradients are the principal determinants of the type and extent of wall rock alteration, and that hydrothermal fluids are at least fundamentally similar, then the particular altered wall rock mineral assemblage, that is reaction products, must be largely governed by number 1, the types of alteration reactions that actually proceed, number 2, WallRock composition, number 3, the pressure and temperature of the environment. Reactions that are important to alteration are many types. They are hydrolysis, hydration dehydration, alkali or alkali earth metasomatism, decarbonation, silication, desilication, oxidation reduction, and finally, a number of addition removal interactions such as carbonatization, desulfidation, sulfidation and fluoritization. Hydrolysis refers specifically to the involvement of H+. It is profoundly important because hydrolysis of WallRock minerals serves both to convert anhydrous silicates like the feldspars to hydrolyzed silicates like the mica and clay minerals, and to buffer the pH of the fluid, in turn affecting solubility and association dissociation relationship in it. In reactions of the following type, that is potash feldspar plus 2H plus ion giving rise to muscovite and quartz and cerisite. Next reaction is the albite plus 2H plus ion giving rise to paragonite plus quartz with the release of sodium ion. So, it can be seen that the stability of feldspars, micas and clays and the transfers from rock silicate into solution of K plus, Na plus, Ca2 plus, Mg2 plus and other ions is controlled in large part by hydrolysis. These reactions and the minerals involved are obviously an important key to the interaction and mutual buffering of fluids and aluminosilicate wall rocks. The potassium, sodium and calcium analogues function at the same time in the same system. Hydration refers to the removal of molecular water from a fluid into a mineral, and dehydration to its addition to the fluid. Equation 1 to 3 above involves both hydrolysis and hydration. A similar reaction important in seafloor alteration is olivine plus water plus 2H plus ion giving rise to serpentine with the release of Mg2 plus ion. A more direct hydration seen in low temperature alteration of hematite is hematite plus water giving rise to goethite. Dehydration normally occurs as pressure or temperature increases around alteration assemblages. An excellent example is kyanite plus quartz giving rise to propylite with the release of water. Alkali and alkali earth metasomatism are also significant. Magnesium metasomatism, for example, may produce dolomite from limestone by the reaction calcite plus Mg2 plus ion in aqueous solution giving rise to dolomite with the release of Ca2 plus ion in aqueous solution, or chloride from potash feldspar in a rhyolite or arkose by K feldspar plus Mg2 plus ion plus water giving rise to chloride plus potassium with H plus ion. Alkali metasomatism can either cause readjustment of feldspar composition by potash feldspar plus sodium giving rise to albite plus potassium, or result in overall increase in potash feldspar with or without cerisite, albite, with or without paragonite, or a halo of high rubidium by potassium ratios. For example, decarbonation reactions are at the center of skarn formation, whereby silicates and oxides are produced by the removal of carbon dioxide from limestone dolomite sections and the recombination of components. They can be represented by dolomite plus quartz giving rise to dioxide with release of carbon dioxide, or more simply by magnesite giving rise to magnesium oxide with release of carbon dioxide gas. Silicification and silication are also common reactions. Silicification refers to the addition of silica as quartz or one of its polymorphs such as chalcedony, opal or jasper, while silication refers to the process of conversion to or replacement by silicate minerals. Silicification is addition or production of a quartz family mineral, as in the silicification of limestones, that is calcium carbonate plus quartz plus H plus ion giving rise to calcium 2 plus with release of carbon dioxide plus quartz plus water, or as in the simple precipitation of silica in any pore space, that is silicon dioxide in aqueous solution giving rise to SiO2, or as in the breakdown of the orthopyroxene, that is bronzite. Bronzite plus carbon dioxide giving rise to quartz plus magnesite. Silication occurs in contact metamorphism by such reactions as calcium carbonate plus silicon dioxide giving rise to wollastonite with release of carbon dioxide gas, which describes silication to produce diopside from dolomite plus quartz. Desilication, silicification occurs in many scones according to the reaction garnet breaking down to calcium carbonate plus iron oxide plus quartz. Oxidation reduction reactions most importantly affect ferrous, ferric iron and sulfur mineralogies and complexes, but they also impinge upon systems containing manganese, vanadium, uranium and other redox pairs. Two representative reactions are magnetite plus oxygen giving rise to hematite and ferrous iron biotite plus oxygen giving rise to potash feldspar plus magnetite with release of water. Sulfur ranges in valence from S plus 6 in sulfate radicals through 0 in the native sulfur to S minus 2 in bisulfide ions, that is HS minus, hydrogen sulfide H2S and many sulfide minerals. Traces of native sulfur are found where sulfide minerals are oxidized to sulfates in the weathered portions of ore deposits. The reaction is copper sulfide plus iron Fe3 plus sulfate SO4 giving rise to copper 2 plus Fe2 plus sulfate SO4, that is equal to plus S 0 charge. The final reaction type involves sulfidation, fluoridation and a host of additions and subtractions. Ferrous iron biotite plus sulfur giving rise to potash feldspar plus pyrite with release of water, or OH mica plus HF giving rise to F mica plus water, that is hydroxysericite and fluorosericite. During WallRock alteration, although most rock forming minerals are susceptible to attack by acid solution, carbonates, zeolites, feldspathites and calcic plagioclase are least resistant. Pyroxenes, amphiboles and biotite are moderately resistant, and sodic plagioclase, potash feldspar and muscovite are strongly resistant. Quartz is often entirely unaffected. As WallRock alteration is in many cases a relatively rapid and incomplete geological process compared to say regional and contact metamorphism, some of these more resistant minerals may persist as unstable relics in new assemblages more commonly than during metamorphism. The next module of this talk is the types of WallRock alteration and alteration assemblages. The common WallRock assemblages are displayed in figure 1 using ACF and AKF diagrams, whose use is described by Best in the year 1982, Winkler in the year 1979 and other textbooks on metamorphic petrology. Types of WallRock alteration have been described by Mayer and Hemley in the year 1967 and Rose and Burt in the year 1979, from whose work much of the following are drawn. Advanced argillic alteration. This alteration is characterized by dickite, kyalinite, both are hydrosilicate of aluminum, pyrophyllite, again hydrosilicate of aluminum, and quartz. Cerisite is usually present and frequently alunite, pyrite, tourmaline, topaz and zincite also occur. At high temperatures, andalusite may be present. This is one of the more intense forms of alteration, often present as an inner zone adjoining many base metal vein or pipe deposits associated with acid plutonic rocks, as at Butte, Montana in the United States of America and Cerro de Pasco in Peru. It is also found in hot spring environments and in telescoped shallow precious metal deposits. The associated sulfides of the ore bodies are generally sulfur rich. Covellite, digenite, pyrite and enargite are most common. This alteration involves extreme leaching of bases, that is alkalis, from all aluminous spaces such as feldspars and micas, but is present only if aluminum is not appreciably mobilized. When aluminum is also removed, it grades into silicification, and with increasing sericide, it grades onwards into sericitization. The generation of advanced argillic alteration can be very important in developing the high permeability necessary for the circulation of enormous quantities of hydrothermal fluids and vein growth, as given by Brimhall and Ghiorso in the year 1983. Sericitization. In ore fields the world over, this is one of the commonest types of alteration in aluminum rich rocks such as slates, granites, etc. The dominant minerals are sericite and quartz, pyrite often accompanying them. Here sericite is represented by muscovite. Muscovite is stable over a wide pressure temperature field, and these accounts for its common occurrence as an alteration mineral. If potassium is introduced into the wall rocks, then rocks low in this element such as diorites can be sericitized in significant amounts. During the sericitization of granite, the feldspars and micas may be transformed to sericite with secondary quartz as a reaction byproduct, but the primary quartz may be largely unaffected except for the development of secondary fluid inclusions. WallRock alteration is progressive, with some minerals reacting and being altered more rapidly than others. If shearing accompanies alteration or any of the other types of alteration carrying phyllosilicates, then a schistose rock may result. Otherwise, horn felsic like textures develop. With the appearance of secondary potash feldspar and or secondary biotite, sericitization grades into potassic alteration, which is very common in the central deeper portions of porphyry copper deposits as at Bingham Canyon, Utah in the United States of America. In fluorine rich environments, topaz together with zunite and quartz may accompany the sericite to form grayson. Outside the sericitization zone, lower grade intermediate argillic alteration may occur. Thus, sericitization may grade into three types of higher grade alteration and one of lower grade. The next, intermediate argillic alteration. It was formerly known as argillic alteration and given its present name by Hemley and Jones in the year 1964 to avoid any confusion with advanced argillic alteration. The principal minerals are kaolin and montmorillonite, group minerals occurring mainly as alteration products of plagioclase. These may be accompanied by amorphous clays. Clays amorphous to X-rays and commonly called allophane. The intermediate argillic zone may itself be zoned with montmorillonite minerals, dominant near the outer fringe of alteration, and kaolin minerals nearer the sericite zone. Sulfides are generally unimportant. Outwards from the intermediate argillic alteration zone, porphyritic alteration may be present before the fresh rock is reached. Next, porphyritic alteration. This is a complex alteration generally characterized by chlorite, epidote, albite and carbonate. Carbonate includes calcite, dolomite or anchorite. Minor sericite, pyrite and magnetite may be present. Less commonly zeolites and montmorillonites. The propylitic alteration zone is often very wide and therefore, when present is a useful guide in mineral exploration. For example, at Telluride, Colorado in America, narrow sericite zones along the veins are succeeded towards by a wide zone of propylitization. Next type is the chloratization. Chlorite may be present alone or with quartz or tourmaline in very simple assemblages. However, other propylitic minerals are usually present and anhydrite may also be present. Hydrothermal chlorides often show a change in their iron magnesium ratio with distance from the ore body, usually richer in iron adjacent to the sulfide veins, although the reverse has been reported. The development of secondary chlorite may result from the alteration of mafic minerals already present in the country rocks or from the introduction of magnesium and iron, though of course both processes can occur together, as at Azo in Arizona in the United States of America. Chloratization is common in alteration zones alongside tin veins in Cornwall in England. Next type is the carbonatization. Dolomitization is a common accompaniment of low to medium temperature ore deposition in the limestones, and dolomite is probably the commonest of carbonates formed by hydrothermal activity. Dolomitization is associated most commonly with low temperature lead zinc deposits of Mississippi Valley type. These can have wall rocks of pure dolomite. Usually, this rock is coarser and lighter in color than the surrounding limestone. Dolomitization generally appears to have preceded sulfide deposition, but the relationship and timing have been much debated in the various ore districts where dolomitization occurs. Nevertheless, dolomitization often appears to have preceded mineralization, to have increased the permeability of the host limestones and thus to have prepared them, ground preparation for mineralization. Other carbonates may be developed in silicate rocks, especially where iron is available and anchorite may then be common, particularly in the calcium iron environment of carbonatized basic igneous rocks and volcanoclastics. This is particularly the case with many Precambrian and Phanerozoic vein gold deposits. For example, Mother Lode in California in United States of America, where anchorite, sericite, albite, quartz, pyrite and arsenopyrite are well developed in the altered wall rocks. At Larder Lake in Ontario in Canada, dolomite and anchorite have replaced large masses of greenstone. As with the chlorides, there may be a chemical variation in the FeMg ratio with proximity to ore body. The chemical significance of carbonatization may take two different forms. Dolomitization of limestone involves very extensive magnesium metasomatism, but only as a base, that is involving potassium, sodium, calcium exchange process. This is called cation metasomatism, and in this case the mineralizing or pre-mineralization solutions must have carried abundant magnesium. Carbonatization of silicate rocks involve inter alia anion metasomatism with the introduction of bicarbonate rather than phases. Next type is the potassic alteration. Secondary potash feldspar and or biotite are the essential minerals of this alteration. Clay minerals are absent, but minor chlorite may be present. Anhydrite is often important, especially in porphyry copper deposits, example El Salvador in Chile, and it can be formed up to 15% of the altered rock. It is, however, easily hydrated and removed in solution even at depths of up to 1000 meters, so that it has probably been removed from many deposits by groundwater solution. Magnetite and hematite may be present, and the common sulfides are pyrite, molybdenite and chalcopyrite, that is, there is intermediate sulfur metal ratio. Silicification. This involves an increase in the proportion of quartz or cryptocrystalline silica that is cherty or opaline silica in the altered rock. This silica may be introduced from the hydrothermal solutions, as in the case of certified limestones associated with lead zinc fluorite barite deposits, or it may be the byproduct of the alteration of feldspars and other minerals during the leaching of bases. Silicification is often a good guide to ore, example the Black Hills, Dakota in United States of America. At the climax, porphyry molybdenum deposits in Colorado, intensive and widespread silicification accompanied the mineralization. Next type is the feldspatization. This is the term often applied when potassium or sodium metasomatism has produced new potash feldspar or albite unaccompanied by the other alteration products characteristic of potassic alteration. Albitization is found adjacent to some gold deposits, often replacing potash feldspar, example Treadwell in Alaska region of United States of America. The next type of alteration is the tourmalinization. This is associated with medium to high temperature deposits, example many tin and some gold veins have a strong development of tourmaline in the wall rocks and often in the veins as well. The Sigma gold mine in Quebec in Canada has veins that in places are massive tourmaline, and this mineral is well developed in the adjacent wall rock. This is also the case in the granodiorite wall rock of the Cisco mine in Quebec in Canada. At Lalangua in Bolivia, the world's largest primary tin mine, the porphyry host is altered to quartz sericite tourmaline rock. If the altered country rocks are lime rich, then axenite rather than tourmaline may be present. The last type of alteration is other alteration types. There are many other types of alteration. Among these may be mentioned like alunitization, which may be of either hypogene or supergene origin, pyritization due to the introduction of sulfur, which may attack both iron oxides and mafic minerals, hematitization, an alteration type often associated with uranium, particularly pitchblende deposits, bleaching due in many cases to the reduction of hematite, glycinization, a frequent form of alteration along side tin, tungsten and beryllium deposits in granitic rocks or gneisses, phenitization, which is associated with carbonatite hosted deposits and characterized by the development of nepheline, aegirine, sodic amphiboles and alkali feldspars in the areoles of the carbonatite masses. Serpentinization and the allied development of talc can occur in both ultrabasic rocks and limestones. It is associated with some gold and nickel deposits, but where serpentine and talc are developed in limestone, there is generally an interaction of SiO2 and H2O and frequently some magnesium. Finally, zeolitization is marked by the development of stilbite, natrolite, helandite, etc., and often accompanies native copper mineralization in amygdaloidal basalts. Next module of this talk is the influence of virginal rock types. A survey of world literature on the subject shows that WallRock alteration exhibits certain regularity with respect to the nature of the host rock. There are of course exceptions, but certain generalizations can be made. Thus, for example, the most prevalent types of alteration in acidic rocks are sericitization, argillization, silicification and pyritization. Intermediate and basic rocks generally show chloritization, carbonatization, sericitization, pyritization and propylitization. In carbonate rocks, the principal high temperature alteration is scarnification, whereas normal shale slates and sheets are frequently characterized by tourmalinization, especially when hosting tin and tungsten deposits. The next module of this talk is the correlation with the type of mineralization. Boyle in the year 1970 has shown that certain types of mineralization tend to be accompanied by characteristic types of alteration. For example, red bed uranium, vanadium, copper, lead and silver deposits are generally accompanied by bleaching. Vein deposits of native silver are usually characterized by carbonatization and chloritization. molybdenum bearing veins are characterized by silicification and sericitization. Next module is the timing of WallRock alteration. The problem of disentangling age relationship between different assemblages of WallRock alteration minerals in a given deposit can be extremely difficult. Their presence, together with evidence such as crustiform banding, has suggested by many workers that the mineralizing solutions came in pulses of different compositions, that is polyascendant solutions. In some deposits, however, such as Butte, Montana in United States of America, there is a considerable body of data suggesting a single long lasting phase of mineralization and accompanying alteration during the formation of main stage veins. Both mechanisms have probably taken place, and some deposits have been formed from monoascendant solutions, whilst others are the result of polyascendant mineralization, according to Meyer and Hembley in the year 1967. Eighth module of this talk is the distribution of alteration assemblages. Alteration associated with magmatic deposits. WallRock alteration around magmatic segregation and magmatic injection deposits is generally inconspicuous and non-diagnostic. Contacts between ore and wall rocks at most magmatic deposit areas are sharply defined, especially in injection type deposits in which the magma was differentiated at depth prior to emplacement in cold wall rocks. WallRock alteration around injection type deposits is likely to be very thin or absent. Only rarely has the injection been accompanied by or followed by hydrothermal activity. Minor hydration is described around the offset ore bodies of the Sudbury complex in Ontario in Canada. But alteration effects around most magmatic deposits are more aptly described as regional metamorphism than WallRock alteration. A special case is an assemblage called phenite, the result of a process called phenitization, which occurs around most carbonatite intrusions. Phenitization is characterized by the development of nepheline, agerine, sodic amphibose and alkali feldspars in the areoles of the carbonatite masses. These halos present sodium metasomatism, hydrolysis and oxidation with increased sodium, hydrous silicates and hematite. They suggest that hydrothermal activity may be important in generating some ores in carbonatites. Alterations associated with porphyry based metal deposits. Broadly, the spatial arrangement of alteration zones, that is the fabric of porphyry based metal deposits, is one of domal or coaxial arrangement outward and upward from a deep core of potassic alteration. A shell of phyllic merging outward to phyllic argillic or argillic and an outer zone of propylitic material. Phyllic alteration in many districts is generally later and has overprinted an earlier lateral continuum of potassic outward to propylitic. Early alteration is thus characterized more or less alkali metasomatism with minor hydrolysis, with profound hydrolysis hydration developed later as part of the same sequence, amounting as it does to a retrograde collapse of thermal gradients and invasion of meteoric waters. Next, alteration associated with skarn deposit. WallRock alteration products associated with skarn deposits around intrusive masses are extensive in many places and contain conspicuous diagnostic minerals, grassolarite and andradite garnet, wollastonite, epidote and pyroxenes such as Hiddenbergite, salite and salites, amphiboles principally tremolite and actinolite, illwite and idocrase minerals of humite group, serpentine, spinels, scapolite and many others. Both silication and silicification are common. The character of the alteration products depends in large part upon the invaded materials and to a lesser extent upon solution composition. For example, the introduction of siliceous fluids into limestone ordinarily results in such a calcium rich minerals such as wollastonite and idocrase, whereas the invasion of the same fluid into dolomites forms magnesium rich minerals such as serpentine and diopside. The following reactions illustrate possible reactions. Calcium carbonate plus SiO2 giving rise to wollastonite with release of carbon dioxide gas. Dolomite plus SiO2 can give rise to diopside. Shales in igneous metamorphic zones tend to develop the characteristic fine-grained sugary textures of hornfels. Locally, knots of chlorite, andesite, garnet or cordierite form and epidote may be abundant. Volcanic rocks undergo comparable alteration. For example, the abundant andesites and andesitic tuffs of central and northern Chile contain conspicuous epidote near intrusive mosses. Carbonate rocks near intrusions are often thoroughly metamorphized to skarn that consists of various silicate and oxide minerals. Alteration effects around contacts between igneous and sedimentary rocks range in width from less than 1 centimeter to several kilometers. In general, the more extensive the metamorphic metasomatic zone in a mineralized district, the more favorable the area is for ore because heat and hydrothermal fluids have obviously penetrated the rocks. Contact zones that are simply recrystallized and show no other metamorphic effects are said to be dry and they seldom contain ore deposits. Silication is abundant around skarn deposits. Shales which are less permeable and thus not as receptive to ore bearing fluids may be rendered hard and brittle by silication and more permeable upon subsequent fracturing. Silication of sedimentary sections is thus one form of ground preparation, whereby soft, impermeable and unfavorable rocks are made more competent and more receptive to the ore fluids and to the deposition of ores. Next, alteration associated with hydrothermal vein type deposits. Cordilleran vein deposits refers to fault fissure controlled lead, zinc, copper mineralized vein deposits such as Quesapalca in Peru, Superior in Arizona in United States of America, the Mayflower mine in the Park City, Utah in United States of America and many others thought to be related to nearby intrusive activity. Cerisite is the most persistent and abundant alteration mineral flanking Cordilleran vein deposits. Carbonate minerals are also common, especially calcite and dolomite. Siderite, rhodochrosite and anchorite are conspicuous in places. Chlorite, most characteristic of epithermal deposits, may also form around these veins. It commonly develops outside the cerisite envelopes away from the ore. Silica is generally present. At Butte, Montana in United States of America, it is considered that the alteration products were an integral part of the ore mineralization. That is, the alteration of minerals were deposited at essentially the same time and by the same fluids as the ore. Successive zones of cerisitized, argillized and propylatized quartz monzonite lie adjacent to every main stage ore bearing fissures, regardless of its size, attitude, ore mineralogy or relative age. Cerisite is found adjacent to the vein and the clay minerals are between the cerisitized rock and fresh quartz monzonite. Nowhere does the cerisite zone grade directly into fresh wall rock. The sequence of alteration is even more striking in detail. The argillic zone is invariably made up of a kyalinetic phase close to vein and a Montmorillonite rich phase close to the unaltered wall rock. Further, the relative proportions of chemical components change systematically from the vein outward, presenting a graphic picture of the hydrothermal alteration process. The sodium, calcium and silica contents increases. A similar but less striking decrease is also shown by iron and magnesium. These changes reflect the fact that the outermost plagioclase was readily hydrolyzed, releasing silica, calcium and sodium, and that the ferromagnesian minerals were altered to chlorite. Continued alteration leached iron, calcium and magnesium from the Montmorillonite to form kyalinite. Further hydrolysis finally broken down the orthoclase, supplying potassium for the production of cerisite. Sulfur content shows a marked increase near the vein. Iron liberated by the early destruction of ferromagnesian minerals combined with hydrothermally delivered sulfur to form pyrite and both iron and sulfur were added. Silica released from the feldspar was deposited as quartz near the vein. Thus, there was a two-way transfer of ions by diffusion, some ions moving into the wall rock and others moving towards the vein. As long as active fluid circulation continued along the vein, each zone migrated away from the fissure. That is, it grew at its outer edge and simultaneously was encroached upon by the next inner zone at its veinward edge. In alteration assemblage of limestone replacement ores, jasperoid is commonly encountered near veins. It may contain enough trace elements near ore occurrences to be a useful exploration guide, but its mere presence is explorationally significant. Pre-ore dolomitization of limestone followed by the generation of granular sandy dolomite are common around dolomite replacement AG, PB, ZN deposits at Gilman and Leadville region in Colorado in the United States of America. Lowering in the year 1949 recognized 5 stages of sequential hydrothermal alteration in lead zinc silver replacement deposits at Tintic in Utah region in United States of America. The stages are: number 1, an early barren stage during which limestones were dolomitized and volcanics were chloritized. Number 2, a mid barren stage characterized by argillization. Number 3, a late barren stage closely associated with the ore shoots and characterized by jasperoid, barite, pyrite and minor chlorite in the carbonate, quartzite and shales with allophane quartz, barite, pyrite, calcite and minor iron rich chlorite in the volcanics. Fourth, an early productive stage closely associated with ore bodies, but consisting of only an inconspicuous zone of sericite quartz pyrite. And number 5th, the productive stage during which ore was deposited with quartz, sericite and pyrite as products of WallRock alteration. The next module of this talk is the alteration associated with epithermal deposits. Epithermal precious metal bonanza ore deposits are characterized by enormously high and extensive induced permeability along fault and fracture zones. Alteration is commensurately broad and complicated by the fact that retrograde boiling zone can be identified in many ore districts. In general, a feldspar stable zone, that is adularia albite assemblage, occurs at depth. In some ore districts, it extends almost to the surface. Alteration gradually flares upward and outward the surface as structural opening proliferate. Chlorite is one of the most abundant minerals in the wall rocks around epithermal deposits in andesites and in deposits such as the Comstock lode in Nevada in United States of America. The enclosing rocks are extensively and pervasively chloritized to a propylitic assemblage. Sericite is more abundant in latite and rhyolite wall rocks, but even here a thin propylite zone may occur at the margins. In general, the more felsic the host rocks, the higher the overall sericite to chlorite ratio. Other alteration minerals are quartz, alunite, zeolites, chalcedony, opal, calcite and other carbonates along the veins. Argillization may be especially widespread in the wall rocks. Among the numerous layer silicate minerals, nacrite, dickite, kyalinite, pyropylite, yellite and montmorillonite may be present. Probably the most diagnostic minerals are the clays, pyrophyllite, sericite and chlorite in the altered rocks and quartz, locally amethystine, opaline or chalcedonic in the veins. The next module of this talk is an example of WallRock alteration. Pirshko and Hodgson in the year 1988 investigated the alteration beside auriferous quartz veins of the Coniorum mine in the Porcupine camp of eastern Ontario in Canada. The authors recognized in the mafic metavolcanics that form the wall rocks are Number 1, a least altered facies consisting of the regional green schist metamorphic mineral assemblage, which on approaching a vein gave way to number 2, a chloride facies in which the actinolite is replaced by chlorite, albite is progressively replaced by calcite plus quartz plus chlorite, and clinozoisite disappears as sericite develops. And number 3, an anchorite facies zone in which the fresh rock takes on a bleached appearance in contrast to the green color of the chlorite facies rocks. This color change correlates with the appearance of anchorite as the carbonate mineral, its considerable volumetric increase. There are concomitant increase in quartz and sericite as the vein is approached and chlorite decreases. And number 4, a narrow zone occupied by the vein envelope facies. In the last named, chlorite is visually absent. Sericite and quartz are prominent. Anchorite appears to have a higher MgFe ratio and pyrite is significantly developed. The mineral assemblage of the various zones can be considered as metamorphic green schist facies assemblages, which grew under influence of different carbon dioxide concentrations in the interstitial fluid.